But actually, yeah, I have the hard task to explain you quantum in the intersection of AI, and there is a rule of thumb that we are saying that at the end, if you explain quantum computing in a way that everyone understands it, you probably do it incorrect, right? And if you do it correct, probably no one will understand it. So let's keep the quantum computing topic, quantum theory, maybe for some drinks later. Let's focus how we apply it nowadays. So I'm quite excited to show you what we are doing as Quantum Basel. So Quantum Basel is an innovation campus close to the city of Basel. So we are working in the intersection of quantum computing and AI, and together with industry partners, I'm quite happy to show you a little bit of application fields of quantum computing. So now you could ask why we need quantum computing for AI, right? But yeah, so we are thinking that the current AI has a lot of limitations and problems. Yeah? For example, probably you know one of the biggest problems that we are facing with generative AI right now is hallucination. Probably if you type in something on ChatGPT, you get sometimes a convincing answer back, but if you do a double check, you can find out sometimes that's not true. But the message from the AI is quite convincing, so that it can misleading you to accept the answer of the AI. So this is one of the biggest problems that we are facing right now in the field of generative AI. And this kind of problem is really related to the model architectures which we are using right now. So the problem to fix that is pretty hard. Another problem that you can experience with generative AI today is it's really bad in reasoning. Yeah? So even simple tasks that is not a problem for a human to solve, it's a big problem still for the AI. So reasoning, really to be intelligent, is quite hard for the AI. And last but not least, robustness of AI. So if you are changing or you are working with unexpected inputs for an AI, where an AI was not trained on, you really can mislead the AI. Here's a nice example where an AI system was trained to classify animals like a pig, and it's just enough to change a couple of pixels in the image, like around less than 5% of the image, and you can mislead the AI to classify the image with the wrong classification. So this is also a problem that we are facing right now in the field of AI. And as you can see, someone now could argue, okay, Jan, actually what we need is more data and more GPUs, then we can solve the issues, right? But nevertheless, this is also not possible, because if you're taking a look right now, you need a lot of resources to train these large language models. I think the last big large language model from the open source world, the Llama one from Meta, they trained it for a couple of months of at least 20,000 GPUs. So you need a lot of resources, and there are also estimations that, for example, the latest OpenAI models cost around $700,000 each day just for the energy. So, and when we are still scaling up these kind of algorithms or models, I think there is a limit. And next to this is also quite interesting that there are roughly estimations that right now all the large language models are already trained on 90% of the public available data. So just saying, hey, we can solve this issue that I have shown you at the beginning in terms of using more resources, like data or GPUs, probably is not the right way, right? And what we want to show you today is that we as Quantum Basel think the right way could be to introduce a new hardware solution for the problem, which is called quantum computing. So this is a fundamental different technology than a classical computer. It works more or less based on the theories of quantum theory. And at the end, there are big promises around this technology. For example, that you can have a higher accuracy in training AI models on these machines. But you could also think about, there are a lot of evidence right now that it could be also lower the carbon footprint for these kind of AI models. And last but not least, we have seen that you can also really speed up the training times for these large language models, which at the end can further decrease the cost for these models. But, yeah, like always, there are also some challenges for the technology. And one of the biggest one is that we need some kind of error correction for the qubits. But next to this, we have also some limitations for the qubits. So qubits are the computing resources that we need for the quantum device to train a model, etc. So we cannot just easily move a GPT-4 model to a quantum computing machine because we have a fixed amount of qubits right now. So our idea is then, okay, let's take a look away from transformer models. Let's take a look to model architectures that were invented recently that promise to train AI with less parameters. So one of the most promising architectures is liquid neural networks. It was invented at the MIT, and it's quite an interesting architecture. And this has a couple of promises. First of all, it could be increase the performance for machine learning, and next to this, it needs less parameters. Another one is reservoir computing, also a new kind of algorithm that we can use. And this algorithm is really suitable to capture more complex data structures in order to perform AI. So what you can see is our thinking is to use a quantum computer with more or less state-of-the-art model architectures and doing AI, but in a hybrid way. So it means like we are not doing just quantum computing, we have also a classical part there involved. So now we know what we want to do in our experiments, right? Now let's take a look to the use case that we want to apply this kind of technology. And we decided to use time series data sets. And this is also quite promising because there's a lot of evidence that these kind of time series data challenges have a higher return on investment for companies. So anomaly detection could be a use case, but much further use cases you can think about. On the right side, you see some example how a time series data set looks like. So you have always a timestamp with some features, could be the sales forecast, could be potential frauds, etc. So we decided, let's try our solution on a time series data set. So here is our architecture. So at the end, we have designed reservoir computing on a quantum computing, yeah? And as said, our solution is hybrid. We are using liquid neural networks on the classical side, on the classical machine. And at the end, we are using also some really classical AI. So LSTM is a well-known algorithms for time series challenges. And the interesting thing is here that we are not getting out one prediction, so we are using the power of all three models. So we are using a little bit of quantum computing, we are using state-of-the-art algorithms like liquid neural networks, but at the end also some classical AI. And with this concept we are quite optimistic to solve really complex problems. So here's the result, and this is an animation, but let me go through really quickly. What you can see on the right side is, for example, in blue, the prediction of our AI model, so the hybrid one, and in yellow, the ground truth. So we were moving now from left to right with this bar to each data point. And here you will see in our animation what kind of solution was used for this algorithm. So did we use liquid neural networks? Did we use quantum reservoir computing, LSTM, or a classical other machine learning model? So let's get started. As you can see, we are moving from left to right. These are all the predictions that we have done for this test set. And you can see we have a clear winner. It's the liquid neural networks that we have used. And at the end, you can see that we are using at least 5% for the quantum computing part. But this is quite crucial because quantum computing can really help you to tackle complex data structures like outliers in a better way than with a classical machine. So at the end, you can see this was quite powerful because we benchmarked this system against a classical LSTM, and with this we could show at the end that we are 24% better than the classical one. So with this being said, so my colleagues are also here, and if you like to discuss further about quantum computing and how you can apply it also in combination with AI, we have also an expert here for quantum safe encryption, so reach out to me or my clients, let's have a chat, and see you soon, yeah? Thank you.
Thank you, Jan, very much. We have still 2-3 minutes, maybe one question for from the audience regarding quantum computing. Okay, I see a hand.
You didn't really talk specifically about this, but I come from the more blockchain side of things. And then there's a lot of concern about when quantum computers come, they will actually be a big security threat to a lot of blockchain ecosystems today. How do you see this?
I can speak up, or do we have another microphone? Quickly, thank you. So you can look it up. There is a term which is called Q-Day. So if you Google for Q-Day, this is actually the day when we have really the quantum computing advantage. And the saying is, when we have this day, every encryption will fail, right? Because we can crack it with a quantum computer. So this is why a lot of public institutions are working right now on quantum safe encryption. So it's a big, big topic. But when this kind of quantum advantage will come is not clear right now. So it could be tomorrow, it could be another 2 or 3 years. But we think the first quantum advantage will be hybrid. This is why we are doing things like that. So combining quantum computing already with classical machine learning or classical infrastructure, and to achieve right now even a benefit. But coming back to you, the Q-Day will come, and we should better prepare with this. And there are a lot of institutions that are working on a quantum safe encryption approach right now. Further questions?
Maybe one more?
Can AI help the development of AI computing? If yes, do you know how much?
What do you mean exactly?
Well, can you use AI to speed up the development of quantum computers?
Yes.
I'm guessing yes.
Yes. This is already happening because we have 2 big problems right now. This is when you're working with a quantum machine, they have errors in their calculations. And what researchers are doing right now, they're using actually AI to mitigate these errors within the calculations. Something you can really compare with fraud detection to identify where is the error and then mitigate the error. So this is something which is a big topic right now, to use also AI in order to help out quantum computing to achieve further the advantage.